Okay, the next type of problem involving gas mixtures is the case where the gas mixture moves through a steady flow device. In this case, we are going to do an isentropic expansion of an ideal gas mixture through a turbine. Okay, for this problem, we are going to assume not only that it's an ideal gas, but that we also have constant specific heats. Now, of course, we could work this problem in different fashions depending on the type of accuracy that we want. But if we assume constant specific heats, then we can utilize the isentropic relations that have been given to us in Chapter 7. And in particular here, we are going to look at the ratio of the temperatures at the inlet and outlet of this steady flow device will be equal to the ratio of the pressures where they are raised to an exponent that is dependent on the ratio of specific heats. In this case, K minus 1 over K. Now, I've created a table here that gives us the relevant information about the two gases that are in this problem that are moving through this turbine as a gas mixture. Those gases are helium and argon, so we have their molecular weights, 4 and 40 approximately for argon. So argon has a molecular weight that is about 10 times greater than that of helium. I've also listed the specific heat at constant pressure and the ratio of specific heats. Now, of course, there's other quantities. There's CV and there's R, which I could have put them all into this table. And the only reason I didn't is they don't play a role in this problem. Do we necessarily know that a priori to start off with? Sometimes not. So, but you always have the table there in front of you if you need additional information. All right, so the problem is asking us for the work output of the turbine. So we know this from our previous work with gas cycles. We looked at the Brayton cycle, and we were able to write out that the output work of a turbine will be equal to H1 minus H2, if I want to keep the term positive. And we can also write that as CP T1 minus T2. So that's why we're utilizing only CP in this table. Now, we are going to require, well, we can work this problem in a number of different ways. The way I'm going to choose to work out this problem is to determine a average specific heat at constant pressure for the mixture. And I didn't do that in the previous problem. It would probably be good for you to go back and work out that problem using the average specific heat at constant pressure, and which I'm going to show you here, and you can see that the process will work. All right, so the first thing we want to do is write down some of our other known information over here. So we are given at state 1, we know both the pressure and the temperature of the mixture of gases as they enter the turbine. So the mixture pressure is 2,500 kilopascals. They give it in megapascals, but I'm going to know that we're going to be requiring a ratio of pressure, so I'll convert it directly to kilopascals. And the temperature of the mixture is 1,300 Kelvin. Now, when we come out of the turbine, we have a pressure that's been reduced to 200 kilopascals. So we can write that down, but we don't know what the temperature is at state 2. Well, we're going to be able to figure it out, but it's not explicitly given to us in the problem statement. Because, of course, it would vary depending on whether or not we will make ideal gas mixture assumptions, constant specific heat assumptions, etc. Now, we can utilize the equation for constant specific heats, or the flow of isentropic expansion through a turbine for constant specific heats, as long as I know what the gas constant is. Well, in this particular case, the gas constant for both helium and argon is 1.667. So for the mixture, it's also going to be 1.667. So that greatly simplifies the problem. So I can go ahead here and very quickly calculate that T2 will equal T1 times the ratio of the pressures raised to the exponent that is dependent on the ratio of specific heats. So this will give me T1 is 1300 Kelvin. The ratio is 200 to 2500. And this will be 0.667 divided by 1.667, which gives me a final temperature of 473.4 Kelvin. All right, so that's the temperature of the gases when we come out of the turbine, and at the pressure of 200 kilopascals. So we have the temperature. Now the only thing we don't have is what is the specific heat of the mixture. So for the mixture, we can figure out an average specific heat at constant pressure by utilizing the mass fractions of the helium and argon. So what we are told is that we have an equimolar mixture of the gases. So what that means is that we have n number of moles of helium equals the number of moles of argon, which essentially means 1 mole of helium is going to be equal to 1 mole of argon. And we also know that that would mean 4.03 moles, 4.03 kilograms of helium would be in the same, well, so equimolar means that for every 4 kilograms of helium we're going to have 40 kilograms of argon. So to figure out the mass fractions, we can utilize the molar quantities. So we can do it either in mass or moles. The ratios would stay the same. So the mass fraction of helium will equal its molecular weight, 4.003, divided by the total molecular weight of the two gases together. So 4.003 plus 39.948. And the same thing, the mass fraction of argon is, the only thing that changes is the numerator, 39.948, divided by this total number of moles, or total mass. So what I'm assuming is if I have 1 mole of helium and 1 mole of argon, I will then have a mass ratio of 4 kilograms of helium to a total amount of approximately 44 kilograms of total gas. Likewise. So what we get here is that the mass fraction of helium is 0.0911, and the mass fraction of argon, which we could have found out just by subtracting the previous mass fraction from 1, since there are only 2 gases, is 0.90899. All right, so then utilizing that, we can figure out the average specific heat of the mixture. So average Cp of the mixture, which we would then just call Cp sub m, will be equal to, let me just write it here, so Cp m will equal 0.0911 times the specific heat of helium, which is 5.1926, and to this we'll add the mass fraction of argon times the specific heat at constant pressure of argon, which is 0.5203, and this then gives me a specific heat of the mixture that's equal to 0.9458, and the units are again kilojoules per kilogram Kelvin. So I have the temperature at state 1, the temperature at state 2. I now know the specific heat, so I can calculate now that the work out per kilogram of mixture passing through will be equal to Cp of the mixture times T1 minus T2. So this is equal to 0.9458 times the difference in temperature of 1300 minus 473.4, and this gives me a value of 782 kilojoules per kilogram of mass passing through the turbine. All right, so again, if you keep your wits about you, the problems themselves are, I'll say, pretty straightforward. You just have to understand how to evaluate these average properties, these mixture properties, and figure out when it's appropriate to do so. Now, the one thing is, if this problem had been different, in other words, if I was dealing with carbon dioxide and helium and, I don't know, some other gas where they all have different specific heats, you would have had to do the exact same thing. Instead of just figuring out the average specific heat at constant pressure of the mixture, you would have also had to figure out the average ratio of specific heats of the mixture, and you would have utilized that in the isentropic flow equation. All right, so that's the last example that I wanted to do with regards to gas mixtures in chapter 13.